point in our treatment of gas phase reactions and the Gibbs energy and equilibrium constant, we've used expressions that were more or less derived from ideal gases. And I'll remind you that that came about when we expressed the chemical potential, and I'll use that for component alpha, as equal to a reference value for that chemical potential plus RT log of the pressure over a reference pressure. Now, this reference pressure we usually take to be 1 bar. All right, but this is the expression that we would use if we were talking, strictly speaking, about an ideal gas, because that was the origin of this log of P term. All right, what if it's not an ideal gas? Do we have to worry about that? Well, in fact, there are some very important industrial processes that take place at very high pressures. I mean, one of these that you may be aware of is the production of ammonia from nitrogen gas and hydrogen gas. And this is a reaction that typically takes place under hundreds of bars of pressure, and I would have a hard time believing that any of these gases are going to be ideal gases at that pressure. So, in fact, if we really want to understand processes like that, we need to have an idea of how to treat a non-ideal gas when it's in a reaction mixture. Well, we've also learned something about that, though, and we know that, for example, one way we can do this is by defining this fugacity function, and I'll remind you that that was given the symbol F, and that by using this fugacity function we could incorporate all of the non-ideal behavior in the parameter itself, in the way that we define that parameter, and that allows us to maintain equations like this one that are derived from ideal gases. So in other words, this would become an equation that looks something like this, where I've got the chemical potential at temperature and pressure is equal to the reference potential, and this is usually at a function of temperature, plus RT log, and now we would have the fugacity of component alpha divided by its reference fugacity. And again, the reference fugacity we often set equal to 1 bar, so that it's consistent with that. Now, the fugacity has the property that it goes as the partial pressure when this partial pressure is going to 0. So at very low pressures, when we have an ideal gas, the fugacity function becomes the pressure itself. But more globally, the fugacity parameter or fugacity function is a function of both temperature and pressure. So we know that it can vary. I will say also that this fugacity function, it is one component of several in a gas mixture, the way I've written it here. So this is really a partial fugacity, just as we would have this as a partial pressure. But this partial fugacity, because it's a non-ideal parameter, it's a non-ideal function, it will also depend on the composition of the gas. So it's a little bit less easy to typify a partial fugacity than it was to characterize the fugacity of a pure substance. All right, I say that almost parenthetically, but you need to realize that it does require some work in order to get a function that will serve the purpose of a partial fugacity. But now when I plug this in to this expression for the chemical potential, and I use my earlier expressions for the Gibbs energy of a reaction, remember, I could write that as a sum over all the components times the stoichiometric component times their chemical potentials. And now when I write that out in terms of these chemical potentials, I can use this new expression here. And that will give me, first, stoichiometric coefficient times the reference value of the chemical potential. And I guess I should be using alpha here, not A. And then add RT log of f of alpha over its reference value, and I'll just assume that that's going to be 1 bar in general. So this is what I'm going to have, and oops, I left out an important part here. I need the stoichiometric coefficient, and we need to sum over all of the components. All right, so we have this as well. So what that means in effect is that we're going to have a definition for this delta G that will look like this, being again this reference value for delta G plus RT times the sum over these components, and I'll just say that f of the log of f of alpha times V of alpha is going to be equal to the log of F of alpha raised to the V of alpha, same as it was for partial pressures. So I'll end up with an expression for log of Q, and now I'm going to give it a subscript F because it is a function of the fugacities of this particular system. So I'll have fugacity of C raised to its stoichiometric power, fugacity of D, these are the products of our reaction, divided by the fugacities of the reactants. All right, so this would be the generalization of this. All right, now this basically gives us a way to get directly to a new value or a new formulation of the equilibrium constant, because when I set this equal to 0 and solve for QF, what I'll end up with is an expression that says that KF is going to be equal to these fugacities, fugacity of C raised to its stoichiometric coefficient, fugacity of D raised to its stoichiometric coefficient, over A and B. But these will also still be equal to this e to the minus delta r g0 over RT. So this will be, in effect, our operational definition for equilibrium constant when we have a non-ideal gas mixture involved in a chemical reaction. And we sometimes call this the thermodynamic equilibrium constant. And we'll have more to say about that in the next video. But the thermodynamic equilibrium constant is one that now is becoming more and more valid for systems that exhibit non-ideal behavior. Now I want to show you one more thing with this. You may wonder, does this really matter and where does this make a difference? So what I want to do is I want to import some data onto this page. So there it is. And this is data for, in fact, this very reaction up here at the top. So this is the Haber synthesis of ammonia. And what I'm showing here are different values of the total pressure running down this column. And then this is the value of Kp using partial pressures. And this is a value of the equilibrium constant using fugacity. Now, ordinarily, we know that equilibrium constant is a function of the temperature, so it will change with temperature, but all of these are done at the same temperature. The only thing that varies is the pressure. And what we can see is that the equilibrium constant in terms of partial pressures actually changes quite a bit as we increase the pressure. In fact, it gets steadily bigger as we change the pressure. But if we look at the same equilibrium constant in terms of fugacities, where the non-ideality of the gas now is built in, we can see it's not exactly constant, but it actually is much more constant as a value as we move down this column than is the partial pressure equilibrium constant. So in fact, the fugacity does seem to correct for a lot of the non-ideality of this gas and gives us a more or less constant value over a wide range of different pressures that we can use reliably to treat this reaction.